Okay, so I have started the recording. It's 7. Okay, Lavanya, thanks. So I can share my slides. It will be better. Great. So that's perfect. So download this. So hello everyone. Good evening. And it's 7:04, and there are 8 people you can see, including me, of course. So 7 of you are here. So I will start. I won't wait for more. And I think you have seen the first slide itself, which is this one, right? Okay, so I will start. Let me keep it like this only. So welcome to NPTEL Day 4 Reaction Mechanism in Organic Chemistry as usual. And today I will talk about Hammett plot, rho value, little bit of sigma value will be of course there. And all these are from this reference, Organic Chemistry by Jonathan Clayton, Nick Graves and Stuart Warren. Okay. Now let me cross check if I am just someone responds that am I audible or not, or screen is visible or not. Is everything fine?
Yes, sir.
Okay, thank you, Jasmine. Okay, see, there will be people, right? Perfect. So let's go ahead. So I will start with a big figure and then small reaction. So this reaction, let us read the heading. Okay, the Hammett reaction constant rho. So reaction constant rho, and what is this? We will talk little bit, and we will see several use case of this thing. Okay, so in the first reaction, which is shown here, so we are saying that reaction to be investigated. It's a alkaline which minus, you can see in the red color, alkaline hydrolysis of meta and para substituted ethyl benzoate. Let me read it again. So we are interested in a reaction where it's an alkaline hydrolysis of meta and para substituted ethyl benzoate. So what will happen after the hydrolysis? We will get the corresponding basically benzoate, substituted meta or para substituted benzoate. So it will have it's a second order reaction, and so this X, what are the X's are like NO2, metachloro, parachloro, parabromo, which you see the green color dotted points. And we will compare the corresponding benzoic, in place of X there is, imagine there is hydrogen. So ethyl benzoate, simple non-substitutive ethyl benzoate. So that will be KH. So KX is the substituted one and KH will be the non-substituted, that is hydrogen only. So and now let us discuss this plot which is shown here. So based on your classes, like what ma'am has told in the classes, you have been introduced to sigma value, right? So here, if you see the plot in the right side along the x-axis, right side along the x-axis is sigma value is plotted. So sigma, which is right side, uh, last right 0.8, and in the left side x-axis minus 0.6 is noted. So these are the sigma values. So sigma values will be there for nitro, metachloro, parachloro, parabromo, all things will be there. Similarly, in the left side is also there's the negative sign. But in where whatever anyway, so in the y-axis we have a rate of this alkaline hydrolysis of ethyl benzoate, meta and para substituted, and the corresponding rate when x is kh. So this log of kx by kh. Now if we plot this, what we get? A straight line. One second. Please try to join in time, at least 7:5. Please try to join at least 7:5. That would be helpful. And so what we have is that when we have meta nitro, we see that from our basic organic. Please Shomudi try to join at 7:5 at least. So what we see that when we have meta nitro, so the green point comes appears at the top right corner, right? Uh, so basically what it means that it has a sigma value around 0.7 or 0.8, and the rate is high. Rate is high in the sense like 2. 2 is a value of log of kx by kh. So it's a positive value. So okay. So since it's a positive value, we can say that the rate when it is nitro substituted, the rate is high. Of compared to what? Compared to, remember, we are always comparing with the unsubstituted, that is normal, without any substituent, that is hydrogen. So log of kx by kh is value is around coming at 2. When it comes to metachloro, it's we can see the sigma value around 0.4, follow corresponding the x-axis, and you see the log of kx by kh value around 1 1.0. When it comes to electron releasing group, like X is again to para-amine group, NH2 group, para-methoxy group, we see that sigma value is negative here for this substituent, and also the Kx by Kh, this Kx is less compared to Kh. Again, I am saying Kx, rate of the substituted one, is less compared to the Kh. So the log value will be negative here. So that's why we see a negative one. So overall, now whenever I will say about this and what is rho, so we have drawn the plot. So we got the cross point like for different substituent, and then we can fit a straight line. Now this straight line has a slope, right? That slope is called gradient. So this gradient, which is defined by Hammett, is rho, sigma for substituent, rho for reaction. So again, this is Greek, sigma for substituent, rho for reaction. So for this reaction, rho value, I mean the slope of this straight line, the best fitted line is 2.6, meaning that this reaction is higher rate when compared to this when there is a meta nitro meta gluo this substituent. Okay, now let's move ahead. So I will show another plot. Okay, please try to join a little early, at least 7:05. Now what you see, so whenever you will come across this situation, we will try to get 2 or 3 points. So imagine we will have an electron withdrawing group like nitro and electron releasing group like amine or methoxy, and we'll try to guess where the point will be, and then we'll try to get a straight line, and we will see what is the slope is our interest here. Now let's see why it is interest and what can be done with this. So I will make it full screen. I hope. Please read this sentence. At least the first, the red color one. The Hammett reaction constant rho, which I earlier discussed. What it measures the sensitivity of the reaction to electronic effect. So that's what it's saying. So you see in the x-axis there was a different substituent sigma value. So we are talking about the electronic effect. A positive rho value means we have a straight line which slope is positive. So rho is positive. Here the green color one. So it has a log k by log k in y-axis, and sigma is a x-axis. And if we get a straight line like this with a positive rho, so a positive rho value, what it means actually, more electrons. Just a second. So what it means is that, try to understand this, more electron in the transition state than in the starting material. So I will discuss this, don't worry. A positive rho value means more electron in the transition state than in the starting material. So I will show this for the this alkaline hydrolysis of ethyl benzoate, substituted ethyl benzoate. And a negative rho value means fewer electrons in the transition state than in the starting material. So let's discuss in a little bit more clearly. So what I will do, okay, just a second, let me take the Jamboard whiteboard. There you go. So we'll talk about positive and negative rho value. Okay, it's a very simple situation, I hope. And yeah, so I have y-axis, and this is bad. At least this is okay. So I have y-axis here, and then x-axis, and then this is sigma, and this is rho, right? So as I said, so what example we have, alkaline hydrolysis. So let's say our X is here, and this is our ethyl benzoate substituted. Now we have OH. This will undergo attack here, and it will form here. So what we have here, substituent as usual. A tetrahedral intermediate will be formed, OH and O minus, and here OET. So this part is clear. Now, when X is electron withdrawing, like NO2, like NO2 group, so this intermediate will be stabilized by electron withdrawing effect. So this rate will be higher. So Kx will be higher, and then Kh will be lower. Kh is low. So what we have? Sorry, there is a little mistake. So this is not rho. Sorry about that. So this is Kx by Kh and then log of it. So what we have, a sigma value will be a nitro. So sigma value, let's say around here, and the Kx by Kh will be high. So a point I will get here. Similarly, what happens if we do NH2? So NH2 has an electron releasing effect. So the rate will be less here, because this NH2 group, what will do? It will push electron to this carbonyl center. So this rate determining step, which is the nucleophilic attack here, carbonyl center, would be diminished. Okay, so rate will be less, and sigma value, let's say around here. So I will have a point here. So log of Kx by Kh will be negative. So there is a positive sign here, there is a negative sign here. Again, there is a positive sign here, there is a negative sign here. So imagine with the 2 point, if I draw a line, so it will be like this. So this is a straight line, and it has a rho value positive. It's a positive. So this gradient is positive. And what is saying? So in terms of electronic effect, that was there in the slide. So positive rho value means more electron in the transition state than in the starting material. So you see why more electron. So OH minus will attack here. So there will be an increased electron density here. So O minus will be there, and then electron withdrawing effect, like it will come toward this. So overall, this electron will this side. Overall, this molecule having higher electron density. So that's why it is saying a positive rho value means more electron in the transition state than in the starting material. So OH minus is attacking there, and then there is an increase in electron density. And the overall effect is that the benzene ring is getting more electron dense compared to the initial one. That's compared to the starting material. Similarly, I can show in another situation where a negative rho value means fewer electron in the transition state than in the starting material. Both of these cases will appear in several examples, which I'll be showing. So overall, you will try to understand this figure when there will be rho positive, that is slope is positive, and when there will be rho negative. And what it indicates, rho positive means electron flow towards the aromatic ring in the rate determining step, and electron flow away from the aromatic ring in the rate determining step, then rho will be negative. I hope this figure is clear. Now I will ask you several questions which are very easy to follow. Now, before I go there will be a couple of examples which are easy. You see this example. So this is the standard one. So this is the standard one, benzoic acid equilibrium. So I didn't show the H plus anyway, that will be there. So this has a rho value of 1, right? And then you see what is the effect of this COOH when it comes to it is getting separated from the benzene. So remember, when the benzene ring gets more electron density, rho value will be positive. When the benzene ring gets less electron density compared to the starting metal, rho will be negative. Now you see in this case, the dissociation of this first one, the dissociation of this one, in which there is a separator of CH2, there is a methylene group separating the benzene ring. So there will be less electron density flowing towards the ring. So that's why rho value is very small. So 0.5. Again, I am saying when it forms COO2 minus. So because of this methylene group, overall the electron density towards the benzene ring is less. So rho value is very minute, 0.5. What happened if we put it COOH farther away from the benzene ring? The effect is, at least what we expect, is very less compared to that one also. So it is 0.2. You see there are two CH2 group, and then there is very minute or not even very less electron density in the benzene ring coming from the electron density of the carboxylate anion. Okay. Now, if we can make some connectivity like double bond here, so there will be some connection with the benzene ring. This double bond is conjugated through overall benzene structure and then COOH also. So again, this connectivity, what happens? Then electron density can come to the benzene ring. So that's why rho value again increases to 0.5. So when there is one CH2 group, rho value is less from the standard one, it will become 0.5. When there are two CH2 group, it becomes 0.2. If we again give some connection here with a double bond, then again it becomes 0.5. So overall, it is the considering we are in the benzene ring how electron density changing, okay, based upon the substituent here. Now I will read something from the book which will be easy to follow. Please read this. Uh, here, with two saturated carbons between the benzene ring. Please try to understand. See in this figure, my cursor is there. Two saturated carbons between the benzene ring and the carboxylic acid. Between what? Between the benzene ring and the carboxylic acid. There are two CH2 groups. There is almost no effect on pKa. But restore electronic communication. So this word I like, electronic communication. By how? Adding a double bond. With a double bond, rho goes back up again. So we are getting rho back up to 0.5. So that's what we're discussing here. Now we can come to our slide. We'll see some other example. Now see this example. Again, in that carboxylic acid, the negative charge was not directly getting to the benzene ring, because it cannot go directly to the benzene ring. Now see a situation where the negative charge directly can go participate in this benzene ring conjugation, delocalization. So here what happens? OH becomes O minus. But here also delocalization were there. But here the negative charge is there. So it will be more prone. And you see the rho value is positive. And it's not only positive, it is a higher value compared to the other case. Like plus 2.3. You compare it with this carboxylic acid. Here it was 1.0. And you see when there is a directly conjugation, the rho value is increases little bit higher. So plus 2.3. Similar situation can be observed in this equilibrium also, second equilibrium. Here NH3 there was no such situation like the nitrogen is having no lone pair, and this equilibrium has a rho value of 3.2. So remember all these example correspond to X of different substituent like X equal to NO2, chloro, bromo, in meta or para, and then NH2, all these things. You will draw a plot and you will get a straight line which has a gradient rho which is 3.2. So these are the case where some equilibria with positive Hammett rho values. That's it. And then let's come to this point. Now I will give you 1 or 2 minutes to think about it. You have to draw the reaction mechanism and what can be the rho value. First, I already told that reaction with positive Hammett. So it will be positive reaction, positive Hammett rho. You just have to assign some number like from 0 to 7, 8 or 9 or in between, whatever. So I will show the first reaction here. Please note it in your notebook. It's a Wittig reaction, and you see PAR3 and alkene kind of thing, CWET, which is reacting with this carbonyl system and it is forming an alkene. So the question is, what will be the rho value? My partial answer is already given. It will be a positive Hammett rho value. And the task one is you have to draw a mechanism, at least try to guess a redetermining step, and what will be the magnitude of rho. Just some tentative, not asking the exact value. Even I won't be able to give the exact value. So I will give you 1 minute to go with it. I think all of you have noted this reaction. Okay, my slide is already there. View all, admit all. Okay. So anyway, whatever your answer, you have to say it in terms of okay, someone left meeting, 13 people are there. Anyway. Jam. Jeez. So let me draw the reaction here. So this is the reaction. It's a Wittig reaction. Okay. So someone can at least say it in the chat box if you are interested. What will be the rho value? If at least some of you had seen it in the slide, right? First of all, I need a small mechanism like one step or two step. Any suggestion from you guys? So I can see Shaumya, Lavanya, Shomudeep, Jasmine, Shomuranjan, S. Venkateshan, and four others also. Any mechanism how it will happen? Why it will be the sigma, sorry, rho value positive? Rho value is 7. Okay, no problem. Great, thank you. Then else? Any mechanism you are aware of it? Wittig reaction or not? Okay, I think it's 1 minute. Okay. So I will just show the mechanism and then 3 to 4. Okay, perfect, no problem. So I let me draw this benzene ring properly. So what will happen? Basically, this can be this double bond can be written also like P plus and then this negative. This isn't typically light. Okay. So what will happen? It will attack this and it will like this. So what I have is benzene ring. There is O minus here, and there will be phosphorus and then Ar3, this plus, and then COOET. Okay. So this is the intermediate form. So you see, so the negative charge electron going towards this. So overall there is a increasing electron density here. That, but the problem is it is similar to alkaline hydrolysis of ethyl benzoate, not directly to the ring but adjacent to the ring. Similar to the alkaline hydrolysis, try to remember. So again we can automatically can guess if there is a X, which is electron withdrawing effect, so it will have a higher rate, like point will be here. And if it is a NH2 group, so it will have, reduce the rate, so any point will be here. So if we draw this, we expect a rho value of positive. And from the mechanism also we can see there is a electron flow toward the benzene ring. Okay, so that's why, again let me complete the mechanism. So it will attack this, and overall in the second step I am showing directly. Okay, uh, so what will happen, sorry, so control Z, it will bond will come here and this will come phosphine oxide, and it will give us the product. Not it only says pH and then COOET. Okay, this will be the product. Anyway, the product is of not of interest. My point is rho value is positive, which we already told. But since the negative charge is adjacent to the benzene ring but not directly on the benzene ring, so rho value is not that much high. It will be somewhat like 2 to 4. I am giving a high range, so if my assumption will be correct. Okay. So anyway, let's check our things, and which is already come on. Huh. So I had the animation, but it won't work. Okay, so rho value is around 2.7. Now, someone said rho value of 7, around 7. That will be clear within some example. So we will see it here also. Now see the example here. In this example, this is an nucleophilic aromatic substitution. Here again, the mechanism is very similar. But the plus point is that, not plus point, the major fact is there, this nitrogen with its lone pair will attack this ipso carbon of this bromine. what will happen then this, so since there is a direct electron transfer at this ipso position at the ring, so it will have a higher rate, higher rho value compared to the initial example, first example. Okay, so what will happen, so the electron density will be delocalized over the benzene ring, but because of this nitro group, most charge, I am saying most negative charge will be taken up, captured by the nitro group. So it will have also rho value positive, it will be higher from the first example, and if you see the answer, it is lying around 4.9. We would expect a much higher value for this reaction because the electron density directly goes to the ring. Still it's not high because of this NO2 group. The most part of the negative charge is captured by this nitro group. That's why it is around 5. Okay, 4.9. So let me draw the mechanism so it will be easier. Control A, so clear frame. So what we have here, it's a simple reaction, and N double bonded O, there is a plus. If you find any problem with these examples, let me know. If you have any doubt, let me know. So Br. So what we have, NH. Ignore the poor drawing. So it will attack here, and then I can draw several resonating structure, but I am showing the major contributing or the most, how the charge will be separated in atoms. O minus and then O minus. There will be plus charge here. TT good. There will be X here, and there will be two things. One will be bromine, and one other will be nitrogen. Okay, right? I just removed the NH, so hydrogen is not there, so it's okay, perfect. So the negative will come here, and this pi bond will come here, and then it will expel the Br, and you will get the corresponding product. So again, so there is a accumulation of electron, electron density in the ring, but mostly it is captured by this nitro group. So it is not around 7 or 8 or 9. So it will have a around 4.9 or 5. So anyway, the numbers are, we cannot exactly guess the number. What is observed, I am showing. Now I will show another example, which is like very high value. Okay. Now you see this example, the third one. Okay, this it's an interesting example, and there are a couple of things. Uh, I will ask you a multiple choice question based on this reaction. Okay, please draw this reaction in your notebook. Let me also draw it so that I can show it. Br and then 2R, 2AR. Okay, perfect, no problem. Please do it in your notebook so it will be very easy to follow. So I have a system Br and then double bond, an aromatic ring. I am showing as a phenyl ring. Okay, no problem. So this is the system of our interest, and then I have tertiary butoxide in tertiary butanol solvent, no problem. So and then rho value is, this time I will give you the rho value. Okay, so rho value is 9, around 9. I forgot, but it is around 9, I remember. Okay, so the question is, one, it's an SN1 reaction. Two, it's an elimination E2 reaction, or three, addition elimination reaction. Addition elimination. So these are option. Option 1 SN2, option 2 E2, and option 3 addition elimination. So please write your answer in the notebook. And why do you think, how this rho value supports this your answer? Whatever your answer, and please try to justify based on the rho value. Why it is addition elimination reaction, and why it is SN1 reaction, why it's an E2 reaction. I will give you some minutes and you just try to answer it. Okay, there are 11 few. There is 10 actually. Any answer? Shomuranjan, sir, it's nucleophilic substitution on kinelic system SN1 mechanism. Perfect. Anyone else? Please, I mean, I'm not going to say anything. You just try to answer something. It's perfectly fine. If we do mistakes, it's good. So we will learn something. Don't worry, just write it. How do I see all of you? Anyway, anyone else? Shomuranjan and three others. I can't see all of you actually. Okay, Venkatesan. Let's wait for others also. Thank you. Okay, Christina, Soumya, Lavanya, Jasmine, and three others, please. There I can see all of you. Okay, no answer. Okay, perfect. Fine. Okay. Let's see the mechanism. Okay. So one of our friend told it's an SN1 kind of mechanism. Hmm? So if it is an SN1 type of mechanism, so what will happen? What do we expect the rho value? Given we have a rho value positive plus 9.0. Okay. So rho value will form. It's an SN1 type, so there will be a positive charge. Like it will explain there will be positive charge. So if I have a substituent like NO2 or let's say bromo, fluoro, like electron withdrawing group. So what will happen? The rate will be low, right? So it will not allow this positive charge to be stabilized. Hmm? So so if uh, if it is positive charge SN1 type, so then the rho value will be actually negative. So in that case, NO2 will have lower value. NO2 will have lower value kx by kh of log of kx by kh. NO2 will be like here, and then this will be here, and then NH2 group which has a sigma value of negative here, and it rate will be high if it is a SN1, assuming we are it is a SN1. So then the rho value will be negative, but observed rho value is 9 and it's positive, so it cannot be the case. Please try to understand. If it is a SN1 type, we will try to have a positive charge forming, right? And the rho value will be negative. What you observe, rho value positive. So it is not an SN1. Again, it is neither a direct elimination, because in that case the rho value cannot be such high. It will be directly come and then it will directly eliminate. So rho value cannot be that much high. It is rather addition elimination mechanism, only in by which only this high value of rho can be explained. How? Let me show it. So what I will do, I will remove this. So how addition elimination is favoring this. So let me take the red color one. So when it is attacked this position, it will go here and then the double bond as usual. So electron withdrawing group will electron density will flow through this two ring, and this time there is no nitro. If we ignore this nitro group, simple benzene group, it will all this come to this benzene ring. Two benzene ring are there. So what will happen? Let me clearly show it. Okay, just a second. Okay, what will happen? So there will be this bond, this bond. So first it is the addition of tertiary butoxide. Okay, here, and then of course we have bromine here, and then another pH ring is here. Now this will turn back and it will leave. So first addition of this tertiary butoxide followed by elimination of this bromide. So because of this high, this electron coming to this benzene ring, we have a such high value of rho 9.0. Someone is trying to view all, admit all. So anyway, so that's the point. So here we showed that based on the rho value, we can assign this. So it's a 9.0. Now I will show you the more elaborate answer on the book, how it has been explained. Just a second. Please read it with me. Okay. So here I will talk about here. It cannot be SN2 reaction. So I give an SN1. It would have a small rho value. My option was not that. I mean E not E. It cannot be an SN1 reaction, or it would have a negative rho value. It would have a negative rho value. SN1 it would have a negative rho value. It must be an addition elimination mechanism through a benzylic anion delocalized around both benzene ring. That's what I'm trying to say here. So it cannot be SN2. It was not an elimination reaction. It was a substitution, just SN2 or SN1. Okay, the option C1 cannot be there. And it must be an addition elimination mechanism through a benzylic anion delocalized around both the benzene ring. You see the mechanism here, and it goes here. The negative charge is delocalized through both of the AR ring, and that's why it forms. So it can be option E1 is automatically will be wrong of choice. Then SN2 or SN1 or this addition elimination. Okay. So this was the situation for positive rho values. Now I will directly go to, I have less time only, 15 minutes. So let's go to this negative Hammett rho values. These are very easy to follow. Here, the first case, see here electron density will from the benzene ring will go to somewhere else. So overall there's a kind of positive charge or kind of feeling here in the benzene ring. So amine group like NH2 OMe will favor the reaction more. Imagine here, if there is X equal to NH2 at the para position, these reactions will be faster. Whereas if it is NO2 kind of thing, it will have a slower rate. So this in the transition state, what I'm saying in the transition state, this electron at the substrate will be dispersed and it will replace this iodine and thus will form the corresponding ether. So what do we expect? We expect a negative value of rho, and the answer is -1. So this has a negative rho value. Now here this is a typical case of an SN1 reaction. An SN1 reaction will have a rho value of negative. This time the carbocation formed, like chlorine will get dissociate from this CCl bond. There will be positive charge and the electron density will flow from the benzene ring to this carbon center. So that's why if it is an NH2 group, it will have a higher rate. So it will be in the topmost position, left side, and if it is NO2 group, it will have less rate. I mean, rate constant will be less. So it at the below side. So if you draw a straight line, it will have a negative rho value. And what will be happen? Of course, we expect as a higher rho value, but not that much high. I mean, the magnitude I am talking about. Of course, it is negative. So what is this? It's a -4.5. Again, since it is not directly on the benzene ring, so it is not abruptly high. Okay, abruptly high. Now I have another example, I think this one. So these I have been talking like aromatic electrophilic substitution all the time. Okay. So what you see here in this aromatic electrophilic substitution, this mechanism is already discussed in the earlier classes. So you know that there will be an electrophile NO2 plus, and the benzene ring will, this pi electron will attack that NO2 group and it will form a carbocation type intermediate. Okay. So since it is directly on the benzene ring, so electron flowing from the benzene ring to the NO2 group, so therefore it will have a higher rho value in terms of magnitude. Of course it will be negative, right? So aromatic electrophilic substitution, so more the electron dense in the ring, higher will be the rate. So we will have a higher magnitude, of course the rho value will be negative. And what is it? -6.4. So we get a higher rho value. These all are showing that how rho value changes depending upon the reaction and their signs, their sign and the magnitude. All these are important to get a mechanistic interpretation. Okay. Now I have a small rho value. These are already I discussed. When there is no conjugation, or there is the reacting center is different site, different position from the benzene ring. So it will be clear here. For example, here the COO2 ET group is and the benzene ring separated by two saturated carbon atom. So we don't expect a rho value of very high. Okay. So again, it will have a rho value of positive and 0.5 because electron density flowing through this. Okay. And again, here, what do you expect? A rho value. So there is a AR group here. So it's a or is a Diels-Alder reaction. So in Diels-Alder reaction, diene should be electron rich and dienophile electron less. So it's the electron rich. So what we expect, if there is NH2 group, methoxy group in this diene, so we'll have a higher rate. So again, I am saying NH2 group and then MEO group, OMe group. If these are, so diene will be electron rich and the rate will be faster. So as I am saying, so it will have a rho value of slightly negative, but there is no overall charge formation here like in the other cases. So it will have a slightly negative value, minus 0.6. This sign is important. Okay, that's what I'm saying here. Lastly, there is a small this part. So again, it's an interesting example. I like it very much. So here the question is, uh, we have a substrate in between the two product. If we treat it with bromine, we get the product at the right side, and it has the rho value of minus 5.7. As we expect, it will be some form of carbocation type thing. When do we treat it with PHCl? We have a rho value of minus 2.7. Of course, both are negative, meaning that when there is X equal to NO2 group and when X equal to NH2 group, what will be the case? NH2 group will favor. So Kx will be high, then Kh. And whereas NO2 group, it will disfavor. Now, so it's a carbocation type, something will be there, some positive charge forming will be there. Okay. So can you explain what are the different mechanism? So that's why it is saying rho values to discover mechanism. And I will give 1 minute. At least you know the bromination mechanism. So double bond and then bromine. So I see 14 people. Did you get the question? My question is, based on the rho value, what do you expect the mechanism will be? Both the mechanism will be same, or the mechanism will be little bit different? How much different? How it is different? These are the question. Shomuranjan and
Excuse me, sir. Excuse me, sir. What is the second reagent, sir? Bromine is one reagent. Second
uh,
reagent, sir. Second reagent.
pH uh, PHSCl.
Oh, thank you, sir. Thank you, sir.
Check it, check it. I have shown it. Question is this rho value. We have to explain this rho value and the mechanism. So what do we expect? If I explain, I have less time anyway. So from our standard mechanism understanding, bromination reaction, we see. Okay, let me check the answer. In the case of bromonium ion, yes. Okay, you just continue. I will try to draw things here. Please try to understand this. Let me show the reaction again. It's a style. So what happened? I have a system like this and Br2. In normally, if you have a normal alkene like simple like this ray alkene, okay, what we expect, it will form a cyclic bromonium ion. This is normal standard condition. Okay, so this is what we expect. Now Similarly, we can think of a situation like this. We can think of a situation here. That is this. There will be formation of cyclic bromonium ion. We can think of it like this also. Then you see there is a, of course, rho value will be negative. So this is a carbocation type intermediate. So NH2 group will favor, electron density goes from the benzene ring as usual statement. But if it is were the case, if it is forming this kind of cyclic bromonium structure, what we expect, rho value should be less. Rho value should be less because it is not directly on the benzene ring. Someone is trying to add it. Show me a running addition reaction. Okay, let's see. Thank you. So where were we? So if we expect to be like this, we will have a rho value. Of course, it will be negative because there is a positive charge forming here. So, but we cannot expect it to be that much high. So minus 5.7, around 6. So actually, what is happening? This is not going through via such structure. It is not going through this cyclic bromonium structure. Rather, it is forming a direct carbocation, benzylic carbocation. So here what is happening, rather than forming that one, it will form an carbocation here. So now see the carbocation, it is directly involved with the benzene ring. See, so this is directly involved with the benzene ring. So electron flows from the benzene ring to this center. So overall, that's why it has a higher rho value. So it's a higher rho value around minus 6, around minus 0.6, minus 6, sorry. Now, so it is not going through the cyclic bromonium ion. So the second reaction, which has the rho value of less, less in digit, okay. In terms of magnitude, again I am saying in terms of magnitude, minus 2.7, around 3. So here, this reaction is actually forming the cyclic intermediate, cyclic carbocation type. Okay. So here, it is not a direct carbocation, open carbocation, I would say. So here it is forming first and this kind of structure. Okay. So this is forming here. So that's why, since here the pH electron density is not direct similar to this first one. See the first one, that was direct conjugation with this. But here it is not that case. So rho value, the magnitude of rho value is less here. Now in the second step, what happens? Again, it's a carbocation type of intermediate. So this has a higher stability of this carbocation type. And it will move from this side. And what we have, pH, and there is SPH here, and there is Cl. So overall, this shows us that not every time there will be cyclic bromonium ion. Okay. So based on the rho value, we can decipher the mechanism that it is forming via a carbocation like this benzylic carbocation, not a cyclic bromonium ion. Whereas in the second reaction, it is the rho value magnitude is less, and so we expect a cyclic bromonium type. Okay, bromonium type, not bromonium. So this S is there, SPH. So this carbocation will be formed, not carbocation again, I would say. There is no carbon in the positive charge. So, and this mechanism will give us this product. So my point is, so from the rho value, we can decipher the mechanism. We can correctly identify the mechanistic steps. Now, I would like to summarize this here within this slide. So whatever I have talked is mentioned in this slide. Okay, first, if you have a small rho value, -1 to +1, so it means that reacting center is far away. Aromatic, and the reacting part is far away. Aromatic too far away, or no electron change like Diels-Alder reaction. Okay, and then hydrolysis of normal aliphatic carboxylate in which benzene ring is far apart. Two rho values cancel each other out. So this is the one situation. Now come to the right side, black color. So +2 to +4. So here electron flow into transition state. Electrons flow into transition state, or negative charge near ring. So if there is a negative charge near the ring, like alkaline hydrolysis of ethyl benzoate, so there will be, it will be around 2 to 4. loss of conjugation. When it will be very high value, when the negative charge on ring. So if there is a negative charge generation on the ring itself or delocalized round benzene ring, then we can expect a value more than plus 5. That's it is tentative. So you can follow this. In the left side, we can see -2 to -4. When it will happen, electron flow out of transition state like SN2 type, okay, in which O minus was attacking an ethyl iodide. So electron was flowing from the substrate to the other thing. Positive charge near ring. Positive charge when it is near to the ring. Okay, near to the ring or loss of conjugation. When we expect it to be very high negative value, when positive charge on ring or delocalized around the benzene ring. So if there is a positive charge like aromatic electrophilic substitution, that is a for nitration reaction, we show that there is a direct positive charge generation at the benzene ring. So we expect to be very high value, more than -5. Okay. So overall, this part represent, if you try to understand this plot, I mean understand this schema, you can explain any observation you face. Okay, so that is the small thing here. No need to remember any exact number. You try to understand where it is happening. It is adjacent to the benzene ring or it is exactly on the benzene ring, how it affects the substituent. Overall, this all you need to understand the rho value and to decipher the reaction mechanism. And with this I would try like to thank you, and if you have any question just let me know, and I am here.
Sir, excuse me, sir.
Yeah, yes Venkatesh.
In the slide 7,
Hmm.
slide 7,
Hmm.
second reaction, sir. Please explain once again, sir. Please explain.
Here.
Yes, sir. That hydrolysis of tertiary butyl, benzene tertiary butyl
Okay,
chloride.
okay, okay. I will show. It's not that difficult. Just a second. Control A. Sorry, clear frame. Okay. Yeah. So I have a benzene ring and this Cl. Let's see X is here. So first it will form a carbocation, right, Venkatesh?
Yes, yes, sir. Yes, sir.
Ah.
Yes, sir.
Now, what do you expect? If there is a NO2 group or if there is NH2 group, which one rate will be higher? This carbocation formation. Which one? NO2 or NH2?
Yeah, NO2, sir. Nitro, sir.
It will be higher rate.
Because NO2 will withdraw the electron. Okay, sir. Then
NO2 will withdraw electron. So this carbocation will be stabilized or destabilized?
carbocation destabilize.
So rate will be low, right? If the
But
carbocation is
breaking of bond, sir. CCl bond will break easily, no, sir.
no,
With
no,
the
no, no,
NO2.
no, no, no. That is a misunderstanding. You are thinking it wrong. So
Uh-huh.
see this substrate. Okay, imagine I have a transition state like this, and I have a transition state, a small one like this.
Okay, sir.
So when it is NH2 group, this carbocation formation will be much higher, faster. Carbocation is more stable. So the
With the NH2. With
in the
NH2.
intermediate will be more stable because NH2 will flow the electron towards this positive charge. So it will be more stable intermediate. This will form much easily compared to the NO2 case.
Oh, okay, okay, okay.
So
So
that's the
NH2
case.
will stabilize the positive charge.
Exactly. So electron flows towards the center. So electron away from the benzene ring.
Okay, sir. Okay. Okay.
So let
That
me.
is a doubt, sir. That is my doubt.
Okay. So if you remember the plot again, I will say sigma value positive here, sigma value negative here, and there is kx by kh, and then log here. So this is the typical example. Now for NO2, a sigma value positive, and the rate will be slow here. And for NH2 group, sigma value is negative and the rate will be high because the carbocation will be stabilized by the NH2 group. So it will have a rho value around like this. And since the plus charge is adjacent to the benzene ring, it is very resonating, I mean conjugated with the benzene ring. So it will be a little bit in between, like 4 to 5 or 6 like this. So
Thank you,
that's
sir.
why.
Thank you.
Okay. Anyone else?
Thank you, sir.
Okay. Thank you. Arivamurthy, you have any question? Okay, no problem. Anyone else? If you have no doubt, so I will end here. And thank you for joining. Okay,
Thank you, sir. Thank you.
okay, thank you.
Thank you, sir.
You're welcome.